Hello everyone, welcome back to my channel. I hope you're all doing great and ready to learn something interesting today. So today we're going to break down an important organic chemistry topic in a simple and easy to understand way. As you can see, the topic here is factors affecting SN1 reaction. So let's just get started and jump straight into the topic and learn something about SN1 reaction. So before discussing the factors, let's just quickly recall what an SN1 reaction is. SN1 stands for substitution nucleophilic unimolecular reaction. It occurs in two steps. Number one step is the formation of carbocation, in which the leaving group first leaves, which then led to the formation of carbocation. Number second step includes the attack of nucleophile, in which the nucleophile attacks the formed carbocation, which was formed in the first step. The end result of this reaction is a substituted compound in which the leaving group has been replaced by the nucleophile. If we talk about its example, a classic example of this reaction is the hydrolysis of tertiary alkyl halide, for example, tertiary butyl chloride. And when this compound reacts with water, the chloride ion leaves first, forming a stable carbocation, which is the first step of the reaction. Water then attacks this carbocation, and after deprotonation, the final product formed is tertiary butyl alcohol. This is the final product of this reaction, a substituted product. I've already explained this reaction and its mechanism in my previous video. If you'd like to understand it in detail, be sure to check out that video first. Now let's just move on to the topic. You can see I've write down full reaction here and break down its two steps here. The first step is the formation of carbocation, and then second step includes the attack of nucleophile. An interesting point to remember is that in this reaction, water performs two functions simultaneously. First, it acts as a polar protic solvent, stabilizing the carbocation and the leaving group, which favors the SN1 mechanism. Second, it acts as a weak nucleophile, attacking the carbocation after it has formed, ultimately producing tertiary butyl alcohol. So I have write down the first factor here, nature of the substrate. So from both of these steps, we know that the slowest or arduous step is the number one step, which is the formation of carbocation. More stable the carbocation formed, the faster SN1 reaction will be. I write down the preferred order for the reaction, which is 3 degree, then 2 degree, then 1 degree, then methyl group. The reason is that tertiary carbocations are stabilized by alkyl groups through hyperconjugation and inductive effects, while the primary carbocations are highly unstable. For example, tertiary butyl chloride reacts rapidly through SN1 reaction, and methyl chloride hardly goes any SN1 reaction. That is the reason this order prefers in this type of reaction. But even a stable carbocation can't form easily if leaving group refuses to leave, right? So here comes our second factor, which is leaving group ability. As the name suggests, a leaving group is the atom or group of atoms that leaves the carbon atom during the reaction. In an SN1 reaction, the very first and the slowest step is the departure of the leaving group to form a carbocation. Therefore, the easier the leaving group leaves, the faster the carbocation is formed, and consequently, the faster the SN1 reaction proceeds. What makes a leaving group a good leaving group? A good leaving group is the one that can stably exist after leaving the carbon atom. In other words, we can say that it can be able to, or it should be able to accommodate the negative charge without becoming highly unstable. The more stable the leaving group is after departure, the better its leaving ability. Among the halide ions, the leaving group ability follows the order iodine, bromide, chloride, fluoride. It means that iodine or iodide is the best leaving group, while fluoride is the poorest leaving group. For example, if we compare tertiary butyl iodide and tertiary butyl chloride here, both can undergo SN1 reactions, but tertiary butyl iodide reacts much faster than the chloride one because of its size, and because iodide leaves more easily than chloride following the carbocation formation to form more quickly. So from all of this, we can conclude that better the leaving group leaves, the faster the SN1 reaction will be. Now that we have understood the role of the leaving group, let's move on to the third factor, which is the effect of the solvent on the SN1 reaction. Write down the third factor here, which is the effect of solvent on the SN1 reaction. The solvent plays a very important role because it directly influences the formation and stability of the carbocation intermediate. As we already know, the rate determining step in an SN1 reaction is the formation of carbocation. Therefore, any solvent that stabilizes the carbocation and the leaving group will increase the reaction rate. SN1 reactions are usually favored by polar protic solvents. But what exactly are polar protic solvents? These are solvents that contain hydrogen atoms attached to highly electronegative atoms such as oxygen. Because of this, they can form hydrogen bonds and effectively stabilize charged species. Some common examples of polar protic solvents are water, methanol, ethanol, and acetic acid. These solvents stabilizes the carbocation through ion dipole interactions and also stabilize the leaving group such as chloride ion or bromide ion through hydrogen bonding. Since both charged species become more stable, less energy is required for the leaving group to depart. As a result, the carbocation forms more easily and SN1 reaction proceeds at a faster rate. So from this type of factor, third factor, effect of solvent, we can conclude that polar protic solvents increase the rate of SN1 reaction by stabilizing the carbocation intermediate and the leaving group. Now let's move on to the fourth factor, which is the nature of the nucleophile. I write down the fourth factor here, which is nature of the nucleophile. Surprisingly, unlike SN2 reaction, the strength of the nucleophile has very little effect on the rate of SN1 reaction. But why is that? Why doesn't the nucleophile affect the reaction rate? The reason is quite simple. In SN1 reaction, the slow and rate determining step is the formation of carbocation. This step takes place before even the nucleophile attacks. This is the step number 1. The attacking of nucleophile is the step number 2. Therefore, whether the nucleophile is strong or weak doesn't influence the speed of the slower step. Once the carbocation has been formed, it is highly reactive and electron deficient. At this stage, almost any nucleophile present in the reaction can attack it. That is the reason why even weak nucleophiles are capable of participating in SN1 reaction. So it means nucleophile has a very little effect on this type of reaction. Some common examples are water, methanol, ethanol, and ammonia. But if we talk about SN2 reactions require strong nucleophiles because nucleophile attacks the substrate in the same step in which the leaving group departs. Both things are happening in the same step. But in SN1 reaction, the nucleophile only participates after the slow step is complete in the second step. So from this type of factor, we can conclude that the strength of the nucleophile has a little or no effect on the rate of SN1 reaction. Its main role is simply to attack the carbocation once it has been formed. Now let's just move on to the fifth and final factor affecting the SN1 reaction, which is effect of temperature. Now this is our last factor, which is effect of temperature. Like most chemical reactions, the rate of SN1 reaction generally increases as the temperature increases. I've written down it here. But why does this happen? When we increase the temperature, the molecules gain more kinetic energy. As a result, they move faster and collide more frequently. More importantly, a greater number of molecules have enough energy to overcome the activation energy barrier required for the formation of carbocation. This is the reason, as we increase the temperature, the SN1 reaction rate will be greater. We already know carbocation formation is the slowest step and it's the rate determining step in SN1 reaction. Increasing the temperature helps this step occur more easily. But there is an important point here to remember. If the temperature is increased too much, especially in reactions involving tertiary alkyl halides, then the reaction may start favoring elimination through E1 mechanism instead of substitution. This is because elimination reactions are generally more favored at higher temperatures. So what we get to know about this factor is that an increase in temperature generally increases the rate of SN1 reaction. However, very high temperatures may shift the reaction towards the elimination reaction. So the reaction conditions should be chosen very carefully. So that's all about the factors affecting the SN1 reaction. I hope this video has helped you understand why some SN1 reactions occur faster than others and how the factors like nature of the substrate, leaving group ability, solvent, nucleophile, and temperature influence the reaction rate. If you found this video helpful, please like the video, share it with your friends and classmates, and subscribe to the channel for more easy to understand organic chemistry lectures. If you have any questions or suggestions, please feel free to leave them in the comments below. I'll be happy to answer them. Thank you so much for watching. Keep learning, keep practicing, and I'll see you in the next video. Until then, take care and happy studying. Bye bye.